Okay, so this is lecture 5, and we are still discussing existence and uniqueness. In the last class, what we showed is that if we consider the problem x prime is equal to f t comma x, and x at t naught is equal to at x naught, and if f is continuous and Lipschitz, then there exists a neighborhood of point x naught t naught or t naught x naught where solution exists, and we did it via Picard's iteration, right? So we define a set of iterative functions, okay, and we show that they converge uniformly to a function, and then we show that this function, where it converges uniformly, turn out to be the solution. And this also we proved. Now first, today we will discuss the uniqueness. And uniqueness will be in that neighborhood what we basically discussed, right? So the solution, not that solution exists in the for all t minus t naught less than equal to h, where h was basically minimum of a comma b by m, where f was Lipschitz in basically in the rectangle R, which was basically set of t comma x, such that t minus t naught is less than a and x minus x naught is less than equal to b, and m was nothing but maximum of mod f over this rectangle R. Okay, that's how we got the this m got this h. All right, so now to prove uniqueness, the proof is very easy. We'll just use the Lipschitz continuity and use the existence results what we have discussed. Okay, so let us define a set. So set will be I delta. This is a collection of all t's, which is the t minus t naught is less than delta. And let us recall L, which was Lipschitz constant for f. Of f on R. So of course L is a positive number, so you can have a positive number. In particular, if we can choose delta small enough, if L is very large, then delta will be very small. If L is around 1, then delta can also be little bit less than 1. Okay, so but ideally, but this choice is in our hand. Whatever that L is, we can choose a delta. So we choose delta positive such that L multiplied with delta is strictly less than 1. Now this is the important choice, that this has to be less than 1. And not that there is no issue with that. We can always make delta small as because okay, so first thing is that we want a solution to exist on I delta, so delta has to be less than h. And in addition, we can take it much smaller. Smaller delta is not a problem. Okay, so that is fine. All right, now let us assume we have two solutions. assume we have two solutions. That means we'll have two functions x and y such that x prime is equal to f t comma x at t naught at x naught, and similarly function y will be y prime is equal to f t comma y at t naught will be x naught. Okay, so we'll assume that that's what it means to have two different solutions. You have exactly same initial condition, same function f, but you get two functions. Then what we want is, we want to show that x t minus y t is basically equal to 0 for all t. Of course, in particular, we'll do it for all t in basically this set t naught minus h to t naught plus h. This is what we want to show. This is to show. Okay. So now, which is again we have chosen delta, smaller delta, inside this set. Chosen a delta such that this I delta lies inside this set. That is of course reasonable. Then let us note that because x and y are the solutions of the ODE, they also satisfy the integral equation. What integral equation they satisfy? They satisfy xt is equal to x naught plus integral t naught to t f t comma x, sorry, it has to be s x of s ds. Similarly, yt will satisfy yt equal to y naught plus t naught to t f s ys ds. And we need their differences, so we subtract one from another one. So xt minus yt. Now there is a mistake here. This is a mistake. It should be x naught. So let's correct that. So now this will be equal to modulus of integral t naught to t f of s x of s minus f of s y of s ds. And because these are exactly the same number given the initial condition, so they get cancelled. Now this is less than equal to integral t naught to t mod of f s x s minus f of s y of s ds modulus. So I took the modulus inside. Again, f is Lipschitz continuous. So I get this to be less than equal to L integral t naught to t xs minus ys ds. Okay, so far so good. Now let us define, let us note that because x and y are continuous function on I delta, so the maximum of I delta is basically a finite number. Okay, so because it's a finite number, I can take it out. So I get xt minus yt. Of course, here I am assuming that t lies between I delta. T is the element of I delta. Otherwise, I cannot do that. So all the t's are in I delta. So this is less than equal to maximum. I took maximum of this thing out. Okay, and L was out, and what is left is a integral t naught to t ds. which is basically less than equal to L maximum of xt minus yt or I delta, and this is nothing but delta. Why? Because the definition of I delta, I delta is chosen like this. Okay, and in particular L minus L into delta is less than 1. So that means this is like this. All right. So now note that this side is independent of t. This is a constant, this is constant, this is some number, and this depends on t. But because this holds for all t in I delta, I can take maximum this side also. Okay, this is less than equal to L delta maximum of xt minus yt. So this is what we have. Now let's look at these two terms. Either this is equal to 0. So if they are equal to 0, then of course xt is equal to yt for all t in I delta. So the solution will be unique in I delta at least. If they are not, then what you get is we can cancel them out. So in that case you'll get cancellation of these two terms, and what you have is 1 less than equal to L delta, which is a contradiction because delta was chosen, contradiction because delta was chosen something like this. So that means they have to be that means this maximum has to be 0. Okay, so the solution x and y are exactly the same function on I delta. Now the question is that how this I delta can be extended to the whole domain of existence, which was this one. And then it's easy, right? Now h is a fixed number. Okay, and delta, of course, the only condition on delta is due to L. So if L is very large, delta can be small, but nevertheless it's a fixed number. Okay, so delta such that L delta is less than 1 is a positive number, is a positive fixed number. So if I draw on the line this t minus t naught less than h, so let me draw. So let's say I have a straight line and I have t naught here, and let's say this is t naught minus h, let's say this is t naught plus h. Then if delta is no matter what it is, so for example if delta is small number like this, so this is will be I delta. Okay, so first I have proved the existence here. Now what I would do, I would look at one of the boundaries of this domain I delta. So let's take this boundary. Okay, and now I take another I delta, another set which is exactly, let's call it I delta 2, but basically the width of this thing will be just exactly delta, and because delta is independent of h or function f, because L is already fixed on whole domain t naught minus h to t naught plus h, I can keep doing it. So I can cover this thing in a finite number of them. Of course, once I hit the boundary, I have to take the minimum so that I don't go outside this thing. So I can cover it in finite number of them. And solution on this one, initially I have proven to be the same. So I repeat the same argument here from this point onward. Okay, so I should be delta by 2 because I have to go both sides. Okay. So okay, so then I do the same thing here, and because the value here is matching, it will match here, and because value here is matching, it will match here. Exactly the same argument will be repeated. Okay, and width will be delta 2 for each, because note that here we are going one sided, so this will be delta by 2. So this will be delta by 2, this will be delta by 2, because we have to go in both directions. Okay, is this argument clear? And then by repeating this argument, I can get the uniqueness on the whole domain. Uniqueness on T naught minus h to T naught plus h. Yes, any question about this discussion?
So please repeat this like last argument. I didn't get this one.
So once you okay, let me clear some of the thing, and I'll show you one extension. Okay, so that it's clear to you. So currently I have shown that on this thing solution is unique. Okay, now let's take this point, whatever that point is, call it T1. Okay, so that T1 solution is well defined and it's unique up to T1. So now let us consider another initial value problem. Let's call it this number to be x1, and then I'm going to show that from at T0 at T1 I draw another I delta exactly with the same delta what I did in the previous case. So I can show in this region, which is this width of delta 2, I will have a unique solution. Is this part clear?
Yes, sir.
Let's call it I1. Okay. Similarly, I can take this point and I go this with the width delta by 2, and I show that solution is unique in this thing. So that means solution will be unique in this bigger one. Is this part clear?
Yes, sir. Got it.
So now we just have to cover this remaining part. And only thing we should remember, we should never go out of it. So once if your delta by 2 is going out of it, you take minimum of the delta and delta by 2, whatever the leftover part is. Okay. So this way what we are doing is that we are on the each small part we are showing the uniqueness, but because the values are matching at this point, endpoints, and because solution is unique, so this is fine. Okay. So now, so far, whatever results we have discussed, they are local in nature. Why? What do you mean by local in nature? So they were local uniqueness and existence result. So I should write existence first. Okay. They were local in the nature in a way that we are always discussing in the neighborhood of some point. Discussing in a small neighborhood of T naught, x naught. Okay, so the question is that can I say something about the whole thing? Can I say something bigger? And the answer is yes. And let me just say the theorem. This is global existence theorem, and also it gives you the uniqueness exactly with the same argument. It will be clear in a second. Global existence theorem. So here, of course, because we need a global existence, I need to have condition on F to be globally. Okay, so let us consider a domain omega, which is a comma b. Let's maybe use maybe use some of the other notation. C comma d cross r. Note that this is with respect to t, this is with respect to r x. Okay, so this is for t variable, this is for x variable. So of course this is a subset of R2, right? Okay. So now let's assume that F is Lipschitz on omega. So this is, remember that before that we assume that F is Lipschitz only on that R. Here we are assuming that it's Lipschitz on the whole omega. That means for any x and y, that inequality will hold, Lipschitz condition will hold. So assume that F is Lipschitz on omega. So it's a kind of global Lipschitz condition. Then, of course, when I say it's Lipschitz, that means it's also continuous in omega. Let's write it explicitly also. F is continuous and Lipschitz with respect to x. So Lipschitz continuity is with respect to the second variable only, not with respect to the first one. Okay, continuous and Lipschitz with respect to x on omega. Then the initial value problem has a unique solution for all t in C, D. Okay. Let's write the initial value problem explicitly. Initial value problem, x prime is equal to f t comma x at t naught is equal to x naught. For all t in this, for all t naught in this, defined on the whole domain, defined on CD. Okay, that means not only that it will define in a small neighborhood around t naught, that is that edge, but it will, you can extend that, you can continue this process for till holes to fill the whole domain CD. So proof is pretty simple. Let us recall what is that edge we discussed in the local existence. If you recall that as, that is minimum of a comma b by m. Okay, what was this a? Let us draw some pictures so that we can recall what is this a. Okay, okay, this was this a, sorry, yeah, this was this a and this was b was this. Okay, and this was the point which was t naught comma x naught, and then r was basically t comma x, such that t minus t naught is less than a and x minus x naught less than b. Okay, now in this case my r is not like this, my r is a strip. So let us draw that strip again. Right, and this is my C, this is my D. So if you look at the number B, this is infinity. Okay, if you compare these two things, B is infinity. So if I take any t naught here, so H will be basically either this, in this case it will be this because this is a minimum distance to the boundary, or this if t naught happens to be here. So depending on where it is. Okay, so it's minimum of t naught minus C or D minus t naught, because we want symmetry, right? We discussed in a symmetric way, but it won't matter if it's not symmetric, because then you can still do the analysis by just taking for all t. So basically all this discussion comes down to well-defined definedness of Picard iteration. So recall that this thing came in the last lecture because we wanted to make sure that Picard iteration stays inside R. But here, because there is no upper boundary, so they can go wherever they want as long as they stay inside this domain, because upper there is no boundary. They can trajectory can move wherever they want. Of course, they have to be single valued, but as long as they stay inside domain, so this is well defined. So what I'm trying to say is that I don't even need this symmetric argument for H. For any t x n t is equal to x naught plus t naught to t f s x k minus n minus 1 ds. This iteration is well defined. That means it's finite for any t in c comma d. Okay, and as you can check, it's exactly the same proof, because on C and D it's a closed and f is continuous function and bounded. Of course, I have to assume that is bounded, and then that's it. That means the integral is well defined. Okay, so that's it. So once you do that, then you can show that on this closed interval, for any t in this closed interval, these are uniformly continuous, hence they converge. So there is a whole xt defined on the complete interval like this. So, and that will be the solution. The continuity, the uniqueness argument follow exactly the same way what I just proved here. So you can do the uniqueness also in exactly in the same way. Okay. So for the global setting, if you have f which is Lipschitz on omega, where omega is a strip, so these kind of domain are called strips, because of course it's a strip in xt plane. Okay. So if f is uniformly continuous in omega, then the solution will exist on c comma d, a closed interval, and it will be unique. And the proof is exactly just the modification of the proof of the Picard iteration convergence we did for the local case. There is absolutely, you can keep taking that. The only place where we used this thing was the where the well posedness was needed. Sorry, well definedness was needed. Okay, any question about this argument? Any question that by this assumption I extended the local existence in uniqueness to the global existence in uniqueness? Yes? Okay. Now, more important question. So far what we have shown is that if f is continuous, sorry, on omega over r, let's take r, and Lipschitz on r, then unique solution exists. Now, a natural question for a mathematician is, I need all these conditions. I understand that under this condition, this is true, but can I relax some of them? Are all these conditions necessary, or can I relax a little bit? Can I do something? Do I need it to be Lipschitz continuous enough? And answer is no. This is a famous Peano's theorem, which says that if f is continuous on R, then there exists a neighborhood of T naught comma X naught where the solution exists. For example, okay, so first thing is that we are not going to give the proof. And the reason is that it will take me 2 classes to prove it. So also you don't get any, it's not that it will be used somewhere else later on. So let's avoid that. But there is a proof, okay? And you see that if you recall the one test case we did, x prime is equal to x, I think 2 by 3 or something like that, right? 0. Okay. So if you look at this test problem, then note that x2 by 3 is continuous function. So solution will exist by Peano theorem. But because Peano theorem does not say anything about uniqueness, you cannot say that the solution will be unique or not. Okay, so Peano theorem only talks about the existence. So that's why I wrote specifically, I wrote the solution exists. I'm not saying that solution is unique. So in this case, because you can see that x2 by 3 is a continuous function, the solution will exist. Whether the solution is unique, and answer is of course no, because this is not Lipschitz continuous. So Peano theorem does not say anything about uniqueness. It just says the solution will exist. So if f happens to be continuous, you can say that local solution will exist. Of course, the existence proof is not via Picard's theorem. It's a very nice construction of by approximating the ODE with some other ODE, some simple ODEs, and then show some convergence in a weird space, and then you use a very strong functional convergence results for functions and then do it something like that. But that we are not going to do. But so you should keep in mind that because Peano theorem, if f happens to be continuous, then it does not guarantee the uniqueness. Okay, only when you have Lipschitz continuity you can guarantee the uniqueness. Now this raises another question. Is this point clear to all of you? What I'm telling you?
Yes.
Okay, so this should be clear to you that if you want to say uniqueness, you need Lipschitz continuity. So this raises another mathematical question. So we have shown that if f is Lipschitz in x variable, okay, this implies that uniqueness. Question is, other way around, is this true? And answer is no. That means what I'm asking is that if the solution is unique, does this mean that function f has to be Lipschitz? And answer is no. So it's only sufficient condition, it's not a necessary condition. Lipschitz continuity of f for uniqueness of the solution is only sufficient condition, not necessary condition. Let's look at an example. Okay. So I define, and of course I need here now I need to define a function f which is continuous but not Lipschitz continuous. Okay, because if it happens to be Lipschitz continuous, then of course the things will be unique, right? The result will the solution will be unique. So let us define a function f t comma x. This is 0 for t less than equal to 0, x in R. Okay. For 2t, if t is positive, but x is negative. Okay, and then 2t minus 4x by t, if t is positive but for x greater than equal to 0 but less than t square. Okay, so basically we are dividing the whole xt space into different regions. So this will be 2 minus 2t if t is positive but x is bigger than t square. Okay, so do you want me to draw these regions? Do you want me to draw these regions?
Yes, sir, please.
Okay, so HCl is not needed, but okay, let's because it doesn't help in any way. Okay, so basically if you have this, then let's look at the first term for any x but t negative. So this will be this part. So this is t, this is x. Okay, so here everywhere you have 0. Now t positive and x negative, which is here, you have 2t. Okay, and the upper part, the positive quadrant for both the variable, you divide into two parts by looking at t square. Here you have minus 2t, here you have 2t minus 4x by t. Okay, and this curve is x is equal to t square. So is this picture clear?
Yes, sir.
Okay, fine. Now first thing we should always immediately see that this is not a Lipschitz function in x. And to see that, what we look at is ft t comma 0, because we are looking at in the neighborhood of 0. So let's look at t comma 0 minus ft comma t square. Okay. Now this is on the line x is equal to t squared. So we are going to use this value. Yeah, okay, so I should write equality here also. So we are going to use these values. So if you use these values, what you get is this is equal to 40. Okay. Okay. Now this implies that ft minus 0, sorry, ft comma 0 minus ft comma t square by t square, because the difference between x variable is t square, is going to infinity, and this should have been bounded, right, to for f to be Lipschitz continuous. Why it has to be bounded? Note that what you want f t comma x1 minus f t comma x2 by mod x1 comma x2 to be less than L for all x1 x2. Okay, this was the Lipschitz condition, but here it's going to infinity when you take x1 to be 0, x2 to be t squared. Of course, we are making them very close to each other. Okay, so this is not Lipschitz, but it's a continuous function. Okay. So by Peano theorem, there is a solution. Maybe local, but it's okay. By Peano theorem, there exists a solution. By Peano's theorem, there exists a solution. Okay, solution to what problem? Solution to the problem x prime f t comma x at 0 is equal to 0. So in the neighborhood of 0, there is a solution. Now I'm going to show you that the solution, whatever that solution is, will be unique. Okay. Now before I go forward and do that, please note that in this case, if you compute the Picard iterations for this initial value problem, they will be highly oscillatory and they won't converge. For example, if you okay, that you should check, and I'll just give you what they are. So basically what you get is x2n will be equal to t square, and x2n plus 1 is equal to minus t square. So you can see that even point wise they are not converging, so there is no hope that they will converge uniformly. Okay, so the Picard iteration do not converge. Okay, is this part clear? Is this clear?
Yes, sir.
Okay, this you can check, you can just compute the Picard iteration. All right, now let us look at the uniqueness. Let us assume we had two solutions. Let's call it phi and psi. Note that the set of T, which will be basically, you want to collect all the T and theta such that they both coincide. This set is not empty. Sorry, I should be more specific. This theta is okay. I should be careful because I need to set it up properly. Let's just set it up first properly. Now I am taking two solutions. Of course, both these solutions has to satisfy the initial condition, so they will be something like this. Okay. Now if they are different functions, then there will be a number theta. So if phi is not equal to psi, so they will exist a theta such that phi theta is less than psi theta. Of course, it can be other way around also, but let's assume it's this way around. Otherwise, you can argue, you can change them. You can change their order. There is absolutely no issue. Okay. So we are assuming that phi theta will be less than psi theta. Otherwise, psi theta will be less than phi theta. So if they are different function, of course, at some theta, this has to hold. Otherwise, they will be the exactly same function. Now I consider this set S, which is a collection of all time for which this function remains the same. Now what can you say about this set S? This is clearly non-empty. Why it's non-empty? Because 0 belongs to this, right? 0 belongs to this because at 0 they match. And it's closed. Why it's closed? Because both phi and psi are continuous function. So if you subtract one from another one, that is also continuous function, and the set of root of a continuous function is always closed. Okay, so this set is closed. That means what? That means that it will have a supremum. So this implies that supremum of S will be sigma, a finite number. Okay, not only that, this supremum sigma is element of S, and phi sigma, this implies that of course phi sigma is equal to psi sigma. Is this clear so far? Any doubt so far?
Sir, how it is closed?
Thus, if f is a continuous function, then this set x belong to D such that fx is equal to 0 is always closed. Yeah, I'm using this result from calculus. Is this result, you understood this result or not? Yes. Either it will be empty or it will be closed. So how to prove this result? If you have not understood this result, let's try to prove it. Basically, it says that it's a closed means that if there is a sequence in this set S, then the limit is also in that set S, right? Is this definition clear to you? When you say such a set is closed, that you take a sequence in that set and then you show that the limit is also in that set, right? So,
Yes,
it's clear that if you take a sequence in that set, that means fx is equal to will be 0 for all the elements of that sequence. Because f is a continuous function, the limit will, if the limit exists, of course limit has to exist, then of course f of that limit will be the limit of the sequence, okay, which is equal to 0. So that point by definition of this limit will belong to the set S. Okay. So now if that part is clear, now we are in the final to show that they are exactly there is some contradiction if this sigma happens to be less than theta. Okay. So now if you take t is some element in sigma theta, note that theta is the point where these functions do not match. Okay, so by making this choice, and if I take this choice and I show a contradiction, that means this set has to be empty set. Okay, so now if I take this into this, that means because t is bigger than sigma and sigma happens to be the supremum of that set, so phi of t has to be phi of psi of t. So I can draw a picture and explain you if you want. Do you want me to draw a picture and explain you what is going on?
Yes, sir.
Okay, so that will be probably a little bit more helpful in this case. Okay. So let us start. We are looking at 0, 0. So okay, so let us start the point from this point, and we'll have two solutions. Okay, so initially these two solutions might be the same for some time. So other one I draw with green, but at some point of time green will go up. Okay, and this other one will be below this, right? At some point of time this will happen. Now exactly the point where this happens is sigma. Okay, so this is the point sigma. Is this picture clear to you?
Yes, sir.
Yes, sir.
Okay, and this is this set S up to sigma, including sigma, and then I'm taking some t at this point. Of course, initially my theta was this, so I'm taking t above sigma but below theta. So that means, of course, here this will hold. Then clearly it shows that here by mean value theorem, and you can also use mean value theorem to say that because this holds here and at sigma they both were equal, there exists T1 in, of course, t comma theta. Okay. I don't need actually t comma theta also. Somewhere this will exist. Let's undo that. There exists t1 such that phi prime t1 will be less than psi prime t1. And that is obvious because you can see that upper function has to increase faster than the lower function, right? Because they started at the same value. So by mean value theorem, we can get this result. Is this part clear? Yes?
Yes, sir.
Okay. So if this is clear, then we are done. Now, so I have got a point. So that means there exists a point t1 which is less than theta such that this holds. Then we also note that phi prime minus p psi prime. I just compute using the ODE f t comma phi minus f t comma p psi. Because note that this is bigger than this one, but if you look at f is a decreasing function in x. Either it's independent of x or it's a decreasing function in x. So if you are in this quadrant, this will be greater than 0, greater than equal to 0. So this means that for all t, phi prime t minus p psi prime t has to be greater than equal to 0, which is a contradiction. Okay, which is a contradiction because by arguing that they are different function, we got this thing. So this can never happen. That means this set is the whole domain, or that means this theta does not exist. Now why this happens? This happens because f is a decreasing function. So we don't know whether f is Lipschitz or not. So in this case exactly we know that f is not Lipschitz, but we are able to show that because f is decreasing, we are able to exploit that property and show that solutions are unique. So even if f is not Lipschitz, you can exploit some other property of f and show that f is a so solutions are unique. So it's not necessary that it has to be Lipschitz only. It can be something else also. But if it's Lipschitz is a sufficient, so this says that Lipschitz is a sufficient condition, not a necessary condition. Okay. So I stop at this point of time. I stop the recording and then we can take questions.